Active and reactive power control of synchronous machine. Let's define the machine ports first. There are three ports in synchronous machine. One is mechanical port, which is shaft. The other is electrical port, AC port, belonging armature or stator coils, and the DC port, also known as excitation port. Power in mechanical port is equal to torque times angular speed of the shaft. Since synchronous machines are operated in constant frequency network, applied mechanical power can be changed by using torque. Electric power on DC port can be given as If squared times Rf. That is copper loss in field coils in rotor. Since we apply DC to rotor coils, there is no reactive power. The other electrical port is armature or stator port. That is the main electric port delivering electric power. This power would be active power, can be given as 3 times voltage, current and power factor. And then there would be some reactive power. It can be given as 3 times voltage, current and sine phi. It is summarized here. Applied mechanical power here in terms of torque and angular speed can be delivered to electrical port in stator, and then applied field current generates some reactive power here in stator. It would be lagging or leading. It depends the field current. Our aim is understanding principle of active and reactive power control. So let's assume losses are neglected. There are no mechanical losses and there are no electrical losses. In such a case, applied mechanical power would be equal to developed power or induced power in armature, and it would be equal to terminal power. Applied mechanical input power is equal to 3 times voltage EF sine delta over XS, and it is also equal to 3 times voltage, current and power factor. Let's talk about active power control of synchronous machine. First, assume that machine is operated as a generator on an infinite bus system, and then assume that there is no excitation current change, so induced electromotive force is constant, and all the parameters given in green are constant, and we adjust applied mechanical power by means of torque. That is the equation we have already written. When you change applied shaft power by means of torque, induced power will be changed and electric power on the terminal will be changed. Since green written terms are constant, these change must be compensated by some change in the equation. Here in this equation, sine term must be changed to compensate PM change. In the right hand side, I cosine term must be changed to compensate power change. Delta change is critical because delta is related with stability. Machine can be only loaded if delta is less than 90 degrees. There is a stability limit, Also, there is a machine heating limit. That limit shouldn't be exceeded. To understand the active power control, let's examine the given animation. In the equation we have discussed, EMF was constant, and we have changed applied mechanical power by means of torque. Now I have increased applied torque and I have increased applied shaft power, and there is an increase in delta. Machine can be loaded up to 90 degrees. When you change applied torque to the machine, there is another parameter which is changing. it is current, you see, especially cosine component of the current. I increase applied torque, you see, magnitude of the current will increase, and cosine component of the current increases. That means there is an active power change in terminal, and we are adjusting terminal power by using torque adjustment. Let's talk about reactive power control. Again, machine is operated as a generator on an infinite bus system, and all the losses are neglected, and there is no change in applied mechanical power, so mechanical power is kept constant, and we adjust induced EMF by means of field current. In the equation, all parameters given in green are constant. Applied mechanical power constant, green. This term is constant. This term is constant. Terminal power constant. That means product of EF times sine delta must be constant, and this brings out an asymptotic line I will show in a few minutes, and then I cosine phi must be constant. That is also bring out another asymptotic line I will show in the animation. You know, delta is loading angle, and it is very critical for machine operation. It is related with stability. Machine can be only loaded if delta is less than 90 degrees. Also, during this adjustment, machine heating limits shouldn't be exceeded. Let's examine the animation. In this case, applied mechanical power is kept constant, so applied torque must be kept constant. I will make no adjustment on torque, and then I will adjust only EF by means of field current. That is EF, something written different here in this Tempus project, but in our course E means EF, field EMF. Okay, let's adjust field current and EMF and observe what will change. When you increase field current, here you see there is a change in current magnitude, and there is a change in power angle, phase angle. And here you see there are two asymptotic lines we have mentioned in the equation. I cosine asymptotic line, and that is the EF sine delta asymptotic line. That means EMF must be on this asymptotic line, and current must be on this vertical asymptotic line. Okay, let's increase field current. Although I cosine term is constant, I sine phi term will be changed. Here you see machine is operated as pure ohmic generator, and here you see machine is loaded by inductive loads. By changing field current and EF, you have adjusted reactive power. If you apply under excitation, here you see machine go under capacitive operation. The generator supplies capacitors. Take care again. Current is always on the asymptotic line. E is always on asymptotic line. There is no active power change because we keep torque constant. But there is reactive power change. So reactive power can be adjusted by changing field current. In this slide, you see 380 kilovolt transmission lines in Turkey's national grid. There are multiple nodes. For example, in Konya node, there would be multiple power stations generating electric power, and there are also many load centers. some industrial loads, some domestic loads, and there will be some capacitive, inductive or pure ohmic loads. Behind such a large network, there are multiple generators supplying Turkish national system. Those multiple generators or generating units construct a system called as infinite bus. On an infinite bus system, voltage and frequency are assumed constant. So there are multiple generation units, G1, generator 1, generator 2. All those generators produce some power and reactive powers. And behind these generation units, there are many loads all around the grid. All those generators supply power and reactive power to keep voltage and frequency constant, to maintain constant voltage and frequency network. Let's summarize. Active power control can only be achieved by changing mechanical power. If the machine is operated as a generator, to produce more electric power, you should apply more mechanical input power. If it is operated as a motor, in case there is an increase in mechanical load on shaft, that means there is an increase in electric power on electrical terminals. Reactive power is controlled by field current. Those parameters are the main parameters affecting power control. A change in mechanical power causes some reactive power change, but that power change can be corrected by adjusting field current. Let's check the animation again. Okay, I apply more mechanical input power, so I cosine term will increase and delta increase. Machine generates more electrical output power, and you see it was lagging, and then after generating higher active output, machine go under capacitive region. There is a side effect. When you change generated active power, there is a slight change in reactive power. But that power change can be corrected by field current. Here you see. To maintain constant voltage and frequency network, generators must supply active and reactive power demands. If there are active and reactive power reserves on the slack buses of the grid, governor controllers keep grid frequency constant while supplying active power demand. And automatic voltage regulators keep grid voltage constant while supplying reactive power demand. To keep voltage and frequency constant, active and reactive power demands on the grid must be supplied. If active power demand cannot be supplied, constant frequency cannot be maintained. In such a case, frequency drops. In contrast, if there is an excess supply, frequency will increase. If reactive power demand cannot be supplied, constant voltage cannot be maintained. If there is an increase in inductive loading on grid, there will be voltage drop on the grid. If there is an increase in capacitive loading on grid, voltage of the system will increase. Turkey's national grid is connected to ENTSO-E system. You can check ENTSO-E frequency control from the given site.